Also, thanks a lot to the organizers for giving me the chance to speak here and to present our results on KPZ superdiffusion in a quantum magnet. Yeah, as I said, so the title of the talk is up. It's KPZ superdiffusion. So let me start actually with showing you some interesting pictures. If you compare like a coffee stain, liquid crystals, burning paper, bacterial growth complex, and a snow surface, it seems at first sight like they have nothing in common. But if you squint your eyes a little bit, you can actually see, looking at this surface at the interface, that they might actually share some common features. And it turns out that this is actually not just imagination, it's true. They're actually linked in a very subtle way by a universality. And it's actually a non-equilibrium universality in how the dynamics of these interfaces occurs. And of course, if you have something that is universal, typically that means there is actually a simplified description of these apparently very different systems. And in this case, the simplified description is given by this equation, the so-called KPZ equation, which to me as an experimentalist looks actually very innocent. But if you look a little more closely, this equation that was actually treated, or I think that gets its name from these three gentlemen, Kardar-Parisi-Zhang here, is actually far from being trivial. And the reason is actually that in addition to some linear terms that you would also find in a normal diffusion equation, there's actually a nonlinear term, and you have a stochastic term. So you have a stochastic noise term in this KPZ equation. And just to give you an idea that is really totally non-trivial to treat this, I want to highlight that just very recently in 2014, Martin Heiser was actually awarded a Fields Medal for technical, like contributions to technical methods to solve this equation. And so we're in a very short, in a nutshell, basically, so we're treating here a nonlinear stochastic partial differential equation. And as I already mentioned, the stochastic character together with this nonlinearity actually make this very, very complicated. All right, but what does the KPZ equation actually describe? So basically, if you think back to the previous slide, the KPZ equation describes interfaces, and concretely actually it describes the evolution of a so-called height field, which because of the stochastic term here is actually also a stochastic variable. So it describes the dynamics of a stochastic height field. And I think it's actually best to understand, or it's best to get a bit more intuition to look at a concrete model. So if we look at this so-called ballistic deposition model, which is basically a model where you can imagine randomly dropping little squares, which once they come down and they hit another square, they stick together, then you actually find this KPZ behavior. So in other words, this ballistic deposition model is a toy model that also falls in this KPZ universality class. And so what are actually interesting or relevant quantities that are at play here? Well, obviously, if you have like randomly dropping little squares, even these sticky squares, then if this continues and they drop and drop and drop, there is just a linear growth. There's this height field, and this height field on average will just grow. At the same time, because it's a stochastic process, this height field will have fluctuations. And this is another important quantity that we'll want to remember. And the third thing, and this is also a very important thing, are the transverse correlations. So because of this nonlinearity, which is basically the derivative of the height field along the x direction, which in this case points along this direction, there are actually spatiotemporal correlations that are important in all of these solutions. And so all of these three quantities actually are very crucial for defining this universality class, so-called KPZ universality. So let's look at this a bit more in detail. So what does KPZ universality mean? Well, KPZ universality basically tells you three things. First of all, that these fluctuations of the height field, so basically the roughness here of this interface, with time should scale as t to the beta, where beta is for all models that fall into this universality class given by 1/3. The second thing is related to these correlations, these transverse correlations. So how are fluctuations correlated in space, basically? And here the statement is that they also have the scaling behavior, and the dynamical exponent in this case corresponds to z equals 3/2. And the third thing and last thing actually at this point is that this height field, being a stochastic variable, is actually given by some growth term, which can be linear, but it can also be sublinear. And it's given by a stochastic variable, so something that fluctuates. And this is actually also a universal distribution here. And concretely, this universal distribution is given by the so-called Tracy-Willem distribution, which is plotted here. So it's a distribution where you have different heights, let's say, on the x-axis and the probability on the y-axis. And you can see that this distribution is actually skewed. So it's the height fields are actually distributed in a non-symmetric way. And this Tracy-Willem distribution is actually also a universal distribution that is very characteristic of the KPZ universality. So these three things basically unite all of these very different models here, which are all basically then in this drawer of KPZ universality. And of course, now what we can do, and this is basically the power of having a universal description, is we can ask, well, what's up with new models? So for example, what's up with the Heisenberg model? Is the Heisenberg model, for example, also part of this universality class? And of course, the definition of the universality class, of the different exponents and the fluctuation of the height field would be things that one has to check in order to verify this. And so in the rest of the talk, this is actually exactly what I want to try to do. I will try to look with you together on the Heisenberg model, on transport in the Heisenberg model to be concrete, and look at whether this is a part of KPZ universality or not. So to do that, I first want to introduce the experimental setup that we work with, and then I want to report on our observation of superdiffusion, and then basically check one after the other the required features to be in KPZ universality. And of course, then we can reach a conclusion after that. So let me start with the experimental setup. So all the data that I'll show you in the rest of the talk were taken in this so-called quantum gas microscope. What is a quantum gas microscope? Well, it's a very good microscope that allows you to take single atom resolved and single spin sensitive images of quantum gases. In this case, the quantum gas is actually trapped in a two-dimensional plane of a three-dimensional optical lattice, and we have control over lattices also in the plane of the atom. So we basically have a two-dimensional system that we can then image with a high-resolution image. Furthermore, we can actually use this quantum gas microscope not only to image the atoms, but we can also control them. So we can manipulate the atom. We can change the spin and also shape the density of the gas. And what you see here on the right is actually an image that we took with this quantum gas microscope. And in the center here, you actually see this very bright bar, let's say. And this is essentially a so-called non-insulating state of atoms where you have single atoms in one atom per lattice side in a very low entropy state. And then you see also some higher entropy regions out here, which we actually use to get to this low entropy in the center by doing some entropy redistribution. And overall, in this image, you see just in the central part in this mod insulator approximately 1,500 atoms. So this is really already quite a sizable quantum system that you can look at with single site resolution, single atom sensitivity. So to give you an idea what this looks like in the lab, just very briefly, we have here two optical tables. One holds the vacuum chamber, which is hidden somewhere in the center here. And then we have an extra table for all the lasers that we need to get the atoms prepared, to cool them, and to put them in this mod insulator state, basically. All right. What are we going to do? Well, in the following, what we're actually going to do is we're going to look at spin chains. So we are going to take these 2D systems that I just showed you, these 2D planes, and then cut them basically into 1D chain. And the way we do that is actually very simple. We can prevent the atoms from moving along one direction and allow them to only move in the other direction. And this actually automatically gives us like one-dimensional chains because all the dynamics in one direction is frozen. What we can also do is we can control the spin state of the atoms. So we have the possibility to, first of all, prepare systems with two different spin states. In this case, they're given as hyperfine states of rubidium-87, so F equals 1, -1, and F equals 2, -2. And we can also control these spin states. Second, of course, what we need in order to realize a Heisenberg model is we need a Heisenberg type spin exchange. And we basically can also engineer that in our optical lattice by going to a regime where we have, on average, one atom per lattice side, and the tunneling of these atoms in this optical lattice is actually much smaller than the interaction of having two atoms on a single side. And in this limit, in the so-called atomic limit, where T over U is much smaller than 1, we actually realize an effective spin exchange coupling, which is basically mediated by virtual hopping processes of atoms on top of each other and then basically exchanging. And taken together, this actually allows us to realize the one-dimensional chains of atoms that interact with this very characteristic Heisenberg model. And actually, I made this slightly more general, so there can actually be an anisotropy in this model, which controls the strength between the spin interaction and the spin exchange. But it turns out that in rubidium-87, this anisotropy is close to 1, just given by the scattering properties and basically given by this exchange process. All right, let me take a step back actually and look at this XXZ chain a little bit more in detail and give you a little bit of background. So the XXZ chain, where this delta doesn't have to be 1, as it is the case in our experiment, it has actually extremely rich transport behavior. So if you look at different deltas, so if you change the anisotropy, you can actually observe ballistic behavior, superdiffusive behavior at the symmetry point where delta is 1, going over into diffusive behavior where the dynamic exponent would be 2, and this happens actually when delta is larger than 1. And there actually have been quite some experiments, of course, not only in cold atoms, but I want to focus on some cold atoms, the realizations of this XXZ model here, and tell you a little bit what was done. So 2 experiments in particular I want to highlight where people actually looked at the relaxation of highly excited spin helix states. So starting from such a mod insulator, what was prepared was like a state that has a certain spin texture that is like looks like a spin helix or spin spiral, and then the system was left to relax. And focusing on this right result here, where the anisotropy of this model was tuned, you can actually see that qualitatively by changing this anisotropy, people found that the dynamic exponents basically match with this expectation. So you crossed over from a ballistic spin transport through a superdiffusive spin transport near the Heisenberg point into a diffusive spin transport. But, and that is actually something that both of these experiments have together, if you look at the Heisenberg symmetry point, where from theory you would actually expect superdiffusive, Z equals 3/2, these experiments observe something that is much more close to diffusive. So this is actually one of the things that prompted us to look back into this problem and actually try to understand what's going on. Furthermore, there is actually, in addition to this discrepancy that that is there between theoretical expectation and these experiments, there was a conjecture that was brought up recently, which is that this symmetry point, this Heisenberg point, is actually very interesting, not only because of it being super diffusive, but moreover because it might be in the KPZ universality class. So in addition to having Z equals 3/2, it might actually have some of the features that I mentioned before, that are shared, for example, then between this model and a stain of coffee. And the question is, of course, how can that be? What does that mean? And I want to show this very briefly with two examples. So what does it basically mean? Transport of the Heisenberg model is in the KPZ universality class. To see that, let's basically first look at the spin chain, and let's focus at the central spin. If we could actually prepare a system with an infinite spin temperature and just keep one spin the same all the time. So for example, prepare this or prepare that state, and so basically change the spin configuration randomly outside of the central spin, and then we were to track the resulting spin density with time, we were actually to find, and this is the prediction, this is the conjecture, a behavior that is consistent with KPZ scaling. So this correlation C here is actually the correlation that you would also find in this ballistic deposition model. And this is actually an extremely non-trivial connection, I think. Unfortunately, it's very tricky to realize an experiment like this, where you have to basically control the atoms at single spin level and have random spin environment on the outside. So it's very hard to realize this experimentally. Luckily, however, these people, Lubotina, Snedarich, and Prosen, also presented another idea, which basically builds on so-called spin domain walls, which are essentially states where you have polarization on one side of the system pointing one direction and the other side of the system pointing the other direction. What you actually need is not like a perfect polarization like this, but you need it also at high spin temperature. So we also need to add some let's say disorder in the spins here, some random spin flips. And now the prediction is that if you follow the relaxation of such a state, and you actually really try to push this to infinite temperature, which means that the contrast of such a spin domain wall goes to 0, you should also find this very characteristic relaxation behavior, which should fall into the KPZ universality class. And the bottom line here is that this seems to be a situation that is actually very feasible to look at in the experiment. This is exactly what we want to do. So question is then, of course, well, what do we need to do to test this KPZ conjecture concretely? Well, this is basically a question that is directly answered by the KPZ universality class and their features directly itself. So we basically have to test exactly the features characterizing KPZ universality. Specifically, what we have to verify is that the dynamical exponent is 3/2. So this is the exponent related with correlations. And the fluctuation exponent is 1/3. And we can also check whether this height function displays the expected asymmetric fluctuations. In addition, there's this first point, which is actually slightly independent of KPZ, but which underlies the conjecture that was made. And we have to basically verify that the system is superdiffusive in the first place. And the superdiffusion requires integrability and SU2 symmetry. So we can also test whether these are here and whether they are actually necessary for superdiffusion. And like these three points here, they actually give us a very clear path towards what we need to check in experiment to test the hypothesis or the KPZ conjecture, namely whether the Heisenberg transport falls into this universality class. And so we set out to do this. And in order to actually realize this proposed idea, first of all, of course, we need to realize this domain wall, the spin domain wall. And the way we do this is we start with this mod insulator. And then we actually use a spin-dependent and spatially controlled light potential to flip the spins in the system. So we flip half of the spins in the system down and the other half up. And the way this looks in the experiment is actually shown here. So if we do this and we just focus at the central part of this mod insulator, you see a system that basically very much looks like a domain where we have many spins up on the left and all spins down on the right. And then we can also image the negative of this. And if we average this, it also looks very nice. Now I told you that we need to actually look at high temperature spin domain walls. And we can also create those actually by adding an additional preparation step, namely rotating these spins away from the spin SC axis and then locally dephasing them. And this actually allows us to basically reduce the contrast of the step, and by that create a higher temperature spin domain one. And then the experiment that we want to do is actually relatively simple. We just want to basically let the atoms go. So we want to quench the system into a non-zero spin exchange and then track the dynamics over time. And just to make this clear, what you see here is basically a parallel, basically 14 1D chains that we can all look at in parallel. So we basically have chains of 50, almost 50 sides length, and we look at 14 of them in parallel. And we check basically how many spins make it over time from one side to the other. And well, this is exactly the program. So what we analyze in the following is basically the polarization transfer of spins moving from one side of the system to the other. And there's actually something that I haven't told you yet on this polarization transfer, which is very interesting, and it's basically a direct consequence of this KPZ conjecture. So basically, the guys, the Butina and others, they worked out a spin correlation function. And now it turns out that if you look at the spin polarization transfer, then this actually corresponds directly to this height field that is described by the KPZ function. And so we can directly relate this temporal dynamics of the spin correlation with the height function, and thus also with this dynamical exponent 1 over c. And so what we do is we basically just evaluate this. To do that, we compare the spin profile at time t with the spin profile at time 0 and just integrate basically the difference between the two. That's the number of transferred spins. And here is the result. If we do that, we see basically a growth. And of course, this growth is given by how the spin profile relaxes. And now the big question is, well, is this growth, like what dynamical exponent does this growth give us? And the result is here. It's of course best looked at in this double log plot. And we see basically that the growth is very well described by a dynamic exponent of z equals 3/2. And actually, if we extract it by a fit, we get something like 1.54. So this is basically the first check mark. We can actually verify the dynamic exponent in the system to be 3/2. And this is already something that, for example, other experiments weren't able to see. Then the second thing that I said we want to check is basically the validity of superdiffusive spin transport at all, or the underlying features of superdiffusive spin transport. And the statement here is that integrability is needed for superdiffusive spin transport to be present. And we can actually check this by breaking integrability. And the way we do this is we just make use of our natural 2D-ness of the lattice. So I told you we have these 14 1D chains in parallel that have like 50 sides length. And we just basically decouple them in order to have 1D systems. But of course, we can also just recouple them. So we can just introduce a vertical tunneling or vertical spin exchange in this case to basically break the 1D-ness of the system and thereby also to break the integrability of the system. And if we do this, the result is shown here. So if we vary the interchain coupling, basically the ratio between J-perp and the in-chain coupling, then we can go from 1D to 2D, from 0 J-perp to J-perp equals to J. And what you see is basically the transport exponent changes from the superdiffusive exponent roughly equals 3/2 to an exponent of 2, which is basically what you expect for diffusive behavior. So this basically shows that in order to get the superdiffusive behavior, which is kind of a necessary requirement for KPZ, we need to be in 1D and we need to be integrable in particular. So that also squares out. Now, the next thing that I told you is that superdiffusive spin transport requires the presence of a symmetry, namely an SU2 symmetry. And in other words, what this means is that the system cannot be globally magnetized. And we can also check this, and I don't have time to go in detail, but in the preparation, we can apply a step which allows us to basically add global magnetization in the system. And the way this works is basically just by offsetting the initial step. the initial spin domain 1. And what we observe in this case is basically shown here. So we have experimental data without magnetization that we saw before, and then with magnetization. And without going into too much detail, first of all, you see a striking difference between the magnetized case and the non-magnetized case. We can also actually extract a ballistic exponent that is not compatible with superdiffusive, and this is exactly what you expect if you break this integrability, basically. So this also squares out. So basically we've, if we break the symmetry, this also squares out. So we've broken the symmetry, and what we observe is not superdiffusive spin transport anymore. So we can also not see KPZ superdiffusion in this system anymore. All right. So now, up to now, basically everything I told you was not exclusive, like it wasn't a smoking gun for KPZ superdiffusion. There's one last feature, which are the fluctuations, which we have to check in order to basically get a smoking gun that that the system is in the KPZ universality class. And why this is so is basically that you can find linear models that share all the features that I just told you about. So they can have a fluctuation exponent of 3/2, and they can actually also change their behavior if you break symmetry or if you break integrability. So in order to really show that the Heisenberg transport is in the KPZ universality class, we actually have to show these asymmetric fluctuations. And specifically, it would be great to show these Tracy-Widom fluctuations. So how do we do this? Basically, here we make use again of the fact that this polarization transfer that we can measure is equivalent to the height field in KPZ in the KPZ equation. And so I told you that this height field is distributed according to Tracy-Widom. And so, of course, now we can conclude, if they're equivalent, that the polarization transfer should also be distributed according to Tracy-Widom. Now, there's actually something that I want to highlight, which is basically in order to do this measurement, we need like single spin counting capability. So this is really something that requires the quantum gas microscope in a sense. So we need to basically be able to get full counting statistics on how many spins have moved from one side of the system to the other. And analyzing this is basically done in this plot. So sorry for the slightly busy plot. I'm going to walk you through it. So what you see here is basically exactly the statistics of spin polarization transfer. So in every shot, we get a certain polarization transfer, and then we can just plot the frequency. And what we analyze now is we analyze basically the symmetry of the distribution, because, as I said, we expect an asymmetric distribution. And the symmetry of the distribution you can actually check by checking the skewness of the distribution, which tells you exactly how asymmetric the distribution is. And what you see here in this plot is basically this resulting skewness for two different configurations. One is this 1D configuration, where we do expect KPZ, and one is a 2D configuration, where we don't. And you see there's a striking difference. The 1D configuration actually keeps its skewness, and the skewness over time. And the skewness is actually also consistent with the Tracy-Widom skewness, which is universal value. And it's actually characteristic for KPZ. And so we take this actually as a very striking evidence, so this fluctuation behavior as very striking evidence for the nonlinearity, and thus also for the fact that Heisenberg transport is in this KPZ universality class. And then finally, one thing that I haven't shown yet, but I told you we should check, is basically this fluctuation exponent beta equals 1/3. So basically, what's the standard deviation of this distribution? We can also check this over time and see how it grows. And this is just done here. And we get on this green data, beta equals 0.31. So that's also consistent, also squares out. And this basically also is another indication, basically, or another piece of evidence that Heisenberg transport is in this KPZ universality. So with this, I'm basically already close to the end. So basically, I was raising this question initially, well, is spin transport, and actually I should be more precise, is T equals infinity, infinite temperature spin transport in the XXZ model at a Heisenberg point in the KPZ universality class. And I hope that I could convince you that we have presented this evidence that this is the case by measuring the dynamical exponent consistent with KPZ, by measuring the fluctuation exponent consistent with the KPZ universality class, by showing that if you break some of the underlying assumptions of superdiffusion and thus also KPZ, the system behavior changes. And finally, also by basically verifying this Tracy-Widom distribution of the polarization transfer and the height function, which we consider to be the smoking gun. And there are many details, of course, to this experiment. And if you're interested, feel free to check out our recent preprint on this topic, which is on the archive. So of course, the question is what next? Well, of course, there are many things that we want to look at. So first of all, we want to understand the fluctuations better. Something I didn't really mention is, for example, a question about different universality subclasses. We want to basically understand the influence of the initial state better, which we also think might be some of part of the discrepancy to previous work on this topic in Paul Adams. And we are actually thinking about checking this universality also in other models, alternative models, for example, this asymmetric exclusion process model. And with this, I'm at the end. I want to thank, of course, the team, especially David Way and Tony, who pushed this project a lot. And of course, Emmanuel and the theory collaborators, Sarang Gopalakrishnan and Norman Yao with his students at Berkeley. It was really a lot of fun to discuss this topic with them. And with that, I want to thank you and happy to take questions.
All right. Thank you, Johannes, for a very interesting talk. I want to remind everybody that to please ask questions in Slack. There's a bit of a delay, but we have just gotten a question. So I'll go ahead and read this to you. This question is from Björn Spiersky. When you take the perpendicular hopping finite, your z climbs up from z equals 3/2 to z equals 2. Does that happen in a crossover? So z equals 3/2 below a crossover time and z equals 2 above?
That is a very good question. So we basically always analyze the full time we have in our experiment. So it's, yeah, so we cannot really see that there is a crossover from one behavior to the other. But I imagine there should be a time scale above which, there should be a time scale above which you get a clear diffusion, probably already when you start breaking integrability straight away. So yeah, a very interesting question, but due to the finite times we have in the experiment, we can actually not really check that.
Okay, and we have another question from Arthur Christianen. What determines the direction of skewness in the distribution? In other words, what breaks the symmetry between the two sides?
Ah, I see. I think it's really just a nonlinearity in the KPZ equation. So I think this is basically the point. You see that if you look at a stochastic equation that does not have this nonlinearity term, you're actually coming out with a symmetric distribution, and only this nonlinearity that you have in the KPZ equation, so the slope derivative squared, gives rise to this asymmetry in the distribution, which I think would intuitively make sense to me. Yeah. So it's just nonlinearity.
Okay, well, thank you once again for your very interesting talk. And at this point, we're going to move into the round table. For everybody in the 2D environment, you can access this on the left side of the screen below the auditorium. And there you'll find Philip and Johannes to answer questions or go into more detail, have some discussions. And I hope to see you all over there.